All right, welcome back. So today we'll be looking into chapter 14, but this is continuance of the topic on induction. So inductance specifically. So at the end of last chapter, we talked about electric motors, and then when the motors coils are spun in the magnetic field, so then as a result, there will be back EMF generated in the coil. Okay, so um, for induction, so look at this circuit here. You have a battery, resistor, and switch, and then you have a coil here in the circuit. Okay, so what happens is that when you flip on the switch, so the switch is on, now you will have current start to flow into this circuit. So current goes from 0 and then to a certain number, right? So once there's current here, there's an induced magnetic field, then will be in the coil here, produced by the coil itself. Now, the coil starts from no current, means no magnetic field, now to have certain magnetic field. So actually, there's a magnetic field change inside the coil here, or in terms of magnetic flux, there's a magnetic flux increasing here. And we learned in the previous chapter that if you have a coil, if the flux through it is changing, then it doesn't like the change. So it will try to oppose to that change, okay? So then the effect will show up here. So as a result, then this coil produces then the induced magnetic field, okay, that is opposing to this guy. So the increase of B field is not all of a sudden to the final value, but it increases actually slowly, okay, because of the back EMF now produced by this coil. And notice I use the term back EMF because that is opposed to the change that caused it. So that's opposed to this is the source that caused the change. So then this guy equivalently, the voltage difference, or we call induced EMF or back EMF, will be in the opposite direction of that guy. Okay. All right. So then, if we have a coil or maybe several coils staying together, so then we have n turns of coil. In the circuit, so once there's a electric current changing in the coil, then there will be back EMF, which result in the back current, back induced current in the opposite direction of the current in the circuit it initially has. Okay. So that effect, the amount of the induced EMF caused by that change. So you can kind of calculate that this should be, again, it's proportional to the change of the magnetic flux over time t, and then in terms of how many number of turns you have in the coil. And it should be proportional to the change of the current as well over time, because if you can imagine, if you have a more change in current, and then you have more induced EMF, okay, proportional to a factor we call inductance of the coil, okay. So then here we introduce the definition for the inductance of the coil, so which is calculated by the induced EMF and then divided by the time change of current over time t, okay, in that case. So L equal to then, you can start from this relationship, take the second here, turn here, and then third turn, they equal to each other, rearrange the turns. Delta t and delta t will cancel. This delta I will come down here, so n times delta phi over delta I. Okay, so this is one way to solve for L. You can also solve for L just using this one and then this guy, okay? So L then equal to absolute value of epsilon induced di over dt. And in if we are talking about just the mathematical equation without the absolute value signs, then we know that induced EMF is minus of di over dt, okay? Because the change of current causes that induced EMF, but it's in the opposite direction according to Lenz's law. All right, so first, let's take a look on a particular example here. It says, what's the rate at which the current through 0.30 Henry coil is changing if an EMF of 12 volt is induced across the coil. So let me see if I have, yeah. So I forgot to mention for the inductance is SI units, it will be according to the equation here. So it will be 1 volt divided by this guy. So from that equation, so 1 volt times second over amps, or it's called Henry. So for the symbol, the unit of the symbol is H. All right, so then this refers to, because this is the unit for the inductance, so that is referred to inductance L. So it tells you L equal to 0.30 Henry, and it's asking you at which the rate, with what rate the current is changing. Okay, F and EMF of 0.12 is induced. So epsilon is 0.12. So that's write down the knowns given here, and then the unknowns we are looking for. So epsilon is being given 0.12 volts. L is given as 0.30 Henry. It's asking us the change of the current, delta I over delta T, okay, or di over dt. Okay, so this is in differential form. This is in the algebra form. All right. So in the previous slide, we know that epsilon is equal to there are two ways, right? So n times delta phi over delta t, or this is also equal to L times delta I over delta t, or di over dt. Let's just say delta I over delta t, okay? Because it looks like this is a constant. So this equal to that. We are given these two, we are looking for this guy. All right, so straightforward. Delta I over delta t then should be equal to epsilon over L. So 0.12 volts divided by 0.3 Henry. So that gives you 0.4. Okay. Amps per second, the change in current. Okay. All right, so let's go back to the slide. Okay, so typically, when you have a coil that is used in the circuit, you have many turns of coil stacking together, and we call it a solenoid. Okay, so for a solenoid, you can imagine if it's in the circuit, like if you have a battery and then resistor and then the solenoid. So inside the circuit, so then once you turn on the switch, so the current goes from 0 to a certain time later I. Okay, so we can look at the whole process from 0 to the final value I. So the B field in the coil increase from 0 to this guy, and that we learned previously, the B field by the current I in the coil. Okay, so mu naught M times I, where N is the number of turns per unit length. So the total number divided by the total length. So then the flux will be equal to N turns times B times A. So B will be equal to that. So that equals to, so this N you calculate from this. Okay, so small n times L will be capital N. N times B, so the M to be squared, and then times A, and then there's a L. Okay. So mu naught N squared I A L. So the flux goes from 0 to this guy, and the current goes from 0 to I. So delta flux. So this delta flux then will be equal to that. And delta I will be equal to that. So we know that you can also calculate L in terms of delta flux over I, right? So then it gives you, so these divided by I, so I goes away. So mu naught N squared A L, okay? So if you go 2 slides back, right? So L could be equal to these together, or in this case, okay, so N times delta phi over delta I. So we have this guy into that already, so that this is the flux through each single coil, but if you have n turns of that, then it's multiplied by n. So in this case, we have n already multiplied by the flux. This is individual flux, and then this is n. Okay, so this should be the total already. All right, so you don't need another m in front of this guy. So when a solenoid is used in the coil in the circuit, it's actually called inductor because it will have inductance, okay, to the coil to the circuit. So this is what you will see typically what an inductor will look like. Okay, so like yeah, you can see that wires is wrapped into many turns here and then also here, and then in this case it's covered by an outside insulator, but in this case also outside insulator. In a circuit, this is a symbol you use in the circuit to represent the inductor. Okay, so it's kind of the spiral shape, but that the coils are stacking together in that sense. All right, so when you have a coil in the circuit, if the current flows in this direction, so then the coil will have a back. So in this case, if it's increasing current, so then it will reduce a current opposite to the increasing. So the current goes now. This is the kind of battery represent the induced EMF. So the current will be going in that direction. So against the original. If current is decreasing, then this guy will be in this direction to compensate the decreasing of current. Okay, so in the current induced is in the same direction of the current that is decreasing. Okay, so this is again according to Lenz's law. For rectangular shape of toroid, toroid is a kind of circular type of coils. You have coils wrapping around on that circular shape. Okay, kind of in this case a rectangular shape. So you can use Ampere's law to calculate what will be the B field. We did this for kind of donut shape circular toroid. Before we figured that the B field is equal to mu naught Ni over 2 pi r, right? So where you do like B integration of B dl, and then through the whole thing that's equal to mu naught times I enclosed. I enclosed will be n times of I number of turns times that. Okay, so then you get this guy. So the flux then through this area you can calculate. So integration of B times dA. All right, so dA and B is a function of R. So then you integrate that. dA will be taking a small slice. Okay, so this guy here for the area. So H times dr. Okay, so integration because there's an inverse of R here. So the result will be a natural logarithm function with the upper limits and then over the lower limits. Okay. So this is the total flux, final flux. So the change will be then equal to this guy minus 0 divided by the change in the current. Okay, so n I minus 0. Okay, so then these divide by that. All right. So in this case, you have now this is just the flux for each of this coil. Okay, for each of coil, you do have to multiply by n because for toroid that amplifies. Okay, so in this case, all right, so then there's mu naught n squared h over 2 pi. Okay, log of R2 over R1. Okay, in the previous case for just inductor, it's also been amplified by the number of n, but in terms of the unit turns per unit length. Okay, so in that case, so that's also n squared, but this here is n squared over here as well. All right. So that's on the self-induction of coils or toroids. Okay, so now let's take a look at mutual induction. That means you have two coils nearby each other. So if there's change of current in one coil, in the second coil, now you can see if there's change in current, then the magnetic field produced by this first one will be changing. Therefore, the magnetic field through the coils in the second second one will be also changing. So then there's flux changing there. So then there will be induced EMF here. So this is called mutual induced EMF. And as a result, there will be inductions in the coil as well to oppose to that change, okay? So the inductance of the coils here are called the mutual inductance. All right, so let's analyze analytically what will be the mutual inductance. And then for mutual induction, we use M instead of just L, okay? So M stands for mutual, M. So if you have two coils, so then the mutual inductance on the second one by the first coil will be equal to number of turns coils in the second times the flux through the coil, each coil in the second. So 2 by 1, okay, and then times I. And similarly, for the other way around, for the mutual inductance on the first one by the second one, you do N1 times phi of 1 by 2 over I2, okay? So then, because this is a mutual inductance, so these guys should be equal to each other. So you'll have this guy equal to that guy. And the induced EMF then on each one of them, if you look at the first one or the second one, either way, so and then you can look at the first one later. So for the second one, you do minus derivative of, okay, N2 phi 21 over dt, okay, so the total flux divided by time dt, right? And then that should be equal to, because N2 phi 21 will be equal to M times I1, that equal to minus dt d over dt of M I1. And then that is equal to minus of M di1 over dt. Okay, so that should be just referring to the change of the current in the first one. Okay, and then epsilon 2, similarly, you can find it out. It's going to be minus M over di2 over dt. Okay, so depends on what you are given. You can use the information as given to find M, or the other way around to find other quantities. Let's take a look on this example. So it says a EMF of 9.7 times 10 to the minus 3 volts is induced in a coil, while the current in the nearby coil, so you have two coils next to each other. So that means we are talking about mutual inductance. So the second coil has rate of current changing, decreasing 2.7 A over seconds, okay? So let's call this as the first one, and then this as the second one. So epsilon 1 equals to minus, we know as M d2 over dt, right? If you go one slice backward, you'll see that. So epsilon 1 is equal to minus M di2 over dt2. Okay, so it gives you this guy, it's asking you for this. Okay, so again, kind of straightforward. You just rearrange the terms. M then equal to minus epsilon 1 over di2 over dt. Okay, so minus of 9.7 times 10 to the minus 3 volts over 2.7 amps per second, but it's decreasing, so minus. So minus and minus will cancel. This one will give you 3.6 times 10 to the minus 3, and that's in Henry. So the mutual inductance should also be in Henry, just as the inductance, okay? All right, so we'll go back to the slide. Next, let's take a look on the energy in the magnetic field, or let's say the magnetic field in the inductor. So we have an inductor in this circuit, and then there's a resistance. So this guy will be now something similar to an RC circuit. In this case, we actually call it an RL circuit, but we will talk about it later. Okay, so in this circuit here, we will use the loop rule from Kirchhoff rules. So you start from here to here, so there's an increase, epsilon naught, and then IR, so it's a drop because you take this clockwise as your loop direction. The current direction is in the same direction through this guy. And then this is always minus of dl times di dl. So epsilon naught minus IR minus L di over dt equal to 0. Okay. So if we multiply everything by I, so then epsilon naught I minus I square R minus L I di over dt. So epsilon naught times I, this is the voltage times I, that gives you the power of by this battery. And then this is also electric power, so I square minus R. So these two terms are having dimensional power. So then this guy has to be also in the dimensional power. So this is the power then by this guy, okay? Or the power delivered to this guy, okay? All right. So let's take a look on that because this is the power delivered on the inductor. We know for inductors, if you have current in them, then there's magnetic field in them. So in this case, the magnetic field in the inductor. So we say the energy is in the stored there in terms of magnetic field. So then you do du by the magnetic field over dt, that should be equal to the power because derivative of time, which is rate of the energy changing, that's the power, okay? dt will cancel, so du is equal to Li di. If you integrate from 0 to um, and then as a result, current goes from 0 to I, so then that gives you how much energy stored in the inductor, okay, as a form of magnetic field. So integration of Li di gives you 1/2 of Li squared. So therefore, energy stored in the magnetic field is equal to 1/2 Li squared. Okay? And with that, let's take a look on this example here. So it says a 10 Henry inductor carries, so L equal to 10. L equal to 10 Henry. The current is 20 amps. How much ice at 0 degree can be melted by the energy stored in the magnetic field of the inductor? Okay, so you have ice T0, T initial equal to 0, and then it's melting, so final will be also equal to 0. Okay, so the melting process. It tells you out the fusion, latent heat of fusion, 334 joules per gram. It's asking you for how much. I'm assuming we are looking for the mass, how much of the ice in grams. Okay, in this case. So energy stored here, EU, M is 1/2 Li squared. That's what we learned just in the past slide. That energy should be converted into the heat, okay, to melt the ice. So melting of ice, that will be M times that guy. So this equal to that, right? So you can set up this guy then equal to that. And then you solve for M. So 1/2 Li squared equal to MLF. M then equal to 1/2 Li squared, L2I squared, divided by LF. So 1/2, 10 Henry, 20 amps squared over 334 joules per gram. So this is gram, so the answer will be in gram, okay? So it gives you 6 grams, okay? So the answer is 6 grams of ice will be melted by the energy stored in the inductor, okay? So you can use that much of energy to melt about 6 grams of the ice. Let's go back to the slide now. Okay. So now let's take a look on a solenoid in the, because that's typically what you use for the as the inductor in the coil in the circuit. So for the solenoid, the B field, the magnetic field in it is equal to mu naught Ni. Okay, and then we learned it before. The inductance is equal to mu naught N square and AL, N is the number of turns per unit length again. So then to calculate the energy stored there in the inductor that has current I, or in the solenoid, which is called inductor, 1/2 Li squared. So L is this, I is B over mu naught M, so that to be squared, okay? So N squared will cancel. My mu naught and mu naught squared will have one mu naught in the denominator remain. So 2 will still remain. On the top here, you should have, now we have this cancel, right? So AL will be still there, B squared will be still there. So B squared AL, okay? A will be the cross-sectional area, L is the length of the solenoid. So basically, A times L will be the volume of the solenoid, okay? Okay, or let's talk about the energy first before we look at the example. So we know in the solenoid, you have this guy, okay? So 2 slides ago, we had that. And then A times L is the volume. So if we divide the total energy by volume, then we get energy density. So lowercase of U sub M, that means the energy in the magnetic field, okay? And that should be equal to, so AL cancel, just B squared over 2 times mu naught. And this then is the magnetic field, the density and energy density in the magnetic field, okay? And in the electricity, when we talk about electric field, it also stores the energy in the capacitor, the electric field in the capacitor. We also conclude that the energy stored in the electric field is 1/2 epsilon naught to the E squared. So in both cases, the energy density is proportional to the field square, and then with a constant number. In this case, the constant number is 1 over 2 mu naught. In this case, the constant number is 1 over 1/2 times epsilon naught, okay? All right, so they are both proportional to the fields square. So let's take a look on the example. So this guy says a solenoid is 10 or 1.8 meters long. So L is equal to 1.8 meters. And the turns is 450 turns. What's the cross-sectional area? So A equals to what? If we know the energy stored is 0.39, so energy is 0.39 joules. The current is actually 12 amps, okay? So you can start with like UM equal to 1/2 Li squared, right? And then B field in the solenoid will be that. So given that L is equal to, if we start from there, mu naught N squared AL, okay? Or if you had the equation already derived in the previous slides, so energy is equal to B squared A times L over 2 mu naught, right? So then you're looking for this A. You can calculate B, or you can do B is equal to, or B squared is mu naught squared, N squared I squared AL over 2 mu naught. So mu naught and the square will cancel. All right. So then this is mu or U instead, okay? All right, so you're looking for area. So you rearrange the terms, that tells you area is equal to 2 times the energy over mu naught N squared, I squared, and L. Then you plug in everything you have. So this N will be equal to, small n is equal to capital N over L, okay? All right. Oh, actually, I think I read it wrong. This is the already small n because it says 450 turns per meter. Okay, so that's already capital N divided by small n. So 2 times 0.39 joules over mu naught is 4 pi 10 to the minus 7 Tesla meters over amps, and 450 per meter squared times I 12 amps squared times 1.8 meters. Okay, so everything comes down to 0.012 meters squared. Okay, so that's the area of the cross section of the solenoid. Okay, all right. So we'll just stop here for today, and then we'll come back next time. So see you guys. Bye.